Section: Introduction. In this section, we discuss how large language models, LLMs, are revolutionizing e-commerce platforms by providing personalized recommendations based on user queries. Unlike traditional search engines, LLMs can not only retrieve relevant information but also present it in a coherent manner. Platforms like Google Search and Microsoft Bing are now incorporating LLM-driven chat interfaces to enhance user experience. Chatbots such as OpenAI's ChatGPT use the internet to gather real-time data for better responses. When a user searches for something, the search engine fetches relevant information from a knowledge base and sends it to the LLM along with the query to generate a response. This process opens up the possibility of manipulating the LLM by influencing the retrieved content. For example, a vendor could strategically insert text to boost their product's visibility in recommendations. We demonstrate how manipulating an LLM can increase a product's chances of being a top recommendation by inserting a strategic text sequence, STS, into the product information. Our framework uses algorithms like Greedy Coordinate Gradient, GCG, to optimize the STS. While such algorithms are usually used for harmful purposes, we show how they can be repurposed to enhance product visibility in a benign way, impacting business and e-commerce positively. By adding the STS to a catalog of coffee machines, we show a significant improvement in the visibility and recommendation chances of the target product. Even when products are already ranked high, the STS can further boost their visibility. This manipulation gives vendors a competitive edge, potentially skewing market dynamics. Safeguards must be put in place to prevent unfair exploitation of AI-driven search tools. Additionally, we touch upon the concept of Retrieval Augmented Generation, RAG, which integrates external knowledge sources with LLMs to improve text generation. Adversarial attacks on LLMs, which involve introducing malicious token sequences to manipulate model outputs, are also discussed. We highlight the importance of studying how LLMs can be influenced to enhance content visibility, especially as they become more prevalent in search engines and e-commerce platforms. Section Summary. In this section, we demonstrate how large language models, LLMs, are being manipulated to increase the visibility of specific products in search engine recommendations by inserting strategic text sequences, STS, into product information. By optimizing the STS using adversarial attack algorithms, we show that the target product's chances of being recommended significantly improve, even when considering variations in the order of retrieved information. This manipulation of LLM search responses provides vendors with a competitive advantage, impacting market dynamics and emphasizing the need for safeguards against unfair exploitation in AI-driven search tools. Section: Strategic Text Sequence. In this section, we explain the LLM-driven search framework and how we create strategic text sequences. Our focus is on online product recommendations. We define the search framework, starting with a user query that triggers the system to gather relevant product details from a knowledge base. These details, along with the query, form a text sequence input for the LLM to generate a tailored response. Vendors can influence this process by adding specific text sequences to their product pages, guiding the LLM to favor their products. In our experiments, we assume the target product information is provided to the LLM for vendor influence. We concentrate on open-source language models like LLaMA2. However, adversarial attack algorithms like GCG can also impact black box models such as GPT-4. We consider a scenario where a user seeks recommendations for affordable coffee machines. The LLM prompt includes the system prompt, product information, list of coffee machines, and the user query. The strategic text sequence, STS, is inserted into the target product's information to guide the LLM's recommendations. We optimize the STS to minimize the LLM's output loss concerning the target product. Initially filled with dummy tokens, the STS is refined using the GCG algorithm, selecting and replacing tokens based on gradients. We assess the LLM with the optimized STS in the target product's information, influencing the recommendations. The STS can impact the LLM's ranking, as seen with Cold Brew Master becoming a top recommendation despite its high price. We analyze the LLM response to rank products accordingly. Experiments focus on the STS's effect on Cold Brew Master and Quick Brew Express rankings. The STS can elevate products in the recommendations, even positioning them as top choices, potentially influencing user decisions. This demonstrates the STS's ability to sway LLM recommendations towards specific products, regardless of user preferences. Section Summary. In this section, we introduce a framework driven by large language models, LLMs, for generating strategic text sequences to influence product recommendations. By concatenating user queries and product information into a single text sequence fed into the LLM, vendors can strategically insert text sequences on product pages to influence the LLM's recommendations. Through experiments, we demonstrate how optimizing these strategic text sequences can significantly impact the ranking and visibility of products in the LLM's recommendations, even favoring higher-priced products over more affordable options. Section: Cold Brew Master. In this section, we ran the GCG algorithm for 2,000 iterations to find the STS for Cold Brew Master. We observed how the rank of the target product Cold Brew Master improved over the iterations, going from not being recommended to becoming the top recommendation in just 100 iterations. By evaluating the effect of the strategic text sequence on the target product's rank in 200 LLM inferences with and without the sequence, we found that adding the optimized text sequence significantly increased the chances of the product being the top recommendation. We then looked at the robustness of the STS to variations in product ordering by randomizing the list of products in the input prompt for 200 independent LLM evaluations. We found that in about 40% of the evaluations, the rank of the target product was higher due to the optimized sequence, while in about 60% of the evaluations, there was no change in the rank. Only a small fraction of the evaluations showed a lower rank due to the optimized sequence. Furthermore, we demonstrated that optimizing the STS to be robust to variations in product ordering could greatly enhance its advantage. By picking a random permutation of the products in each iteration of the GCG algorithm and optimizing the STS tokens accordingly, we found that the resulting STS was much more resilient to changes in product ordering. This led to a significant increase in the advantage percentage and a negligible disadvantage percentage. Moving on to Quick Brew Express, a more affordable option that typically ranked second in the LLM's recommendations without the STS, we showed that adding the STS could elevate its ranking, often making it the top recommended product. Similar to Cold Brew Master, we optimized the STS using the GCG algorithm for 2,000 iterations and observed how the rank evolved over iterations, with the product eventually becoming the top recommendation consistently. By randomizing the ordering of the products in the LLM's prompt and evaluating the effect of the STS using 200 independent evaluations, we found that optimizing the STS with a random ordering of the product list in each iteration of GCG could significantly increase the advantages while minimizing the disadvantages.